Welcome everybody to my talk towards application layer purpose-based access control, which is part of the Privacy by Design in Practice track of the 2020 ACM Symposium on Applied Computing. In this talk, I will primarily focus on the question how the privacy or data protection principle of purpose limitation can be materialized technically, or as we say, by design. For this purpose, I will first discuss why existing or proposed approaches like Hippocratic databases are not broadly adopted in practice. And based on this analysis, I will then demonstrate how the principle of purpose limitation can be materialized technically in line with actual practices from information systems engineering. To provide some context, the work behind this talk is part of an endeavor to establish a more comprehensive view to data protection by design and by default. As we all know, Article 25 of the GDPR obligates controllers to implement technical measures that address data protection principles in an effective manner. And this obligation, of course, depends on factors like the state of the art, the cost that it raises, and so on. More importantly, however, this obligation applies to all principles that the GDPR establishes in Article 5. These principles do noteworthily include aspects like the lawfulness, fairness, purpose limitation, data minimization, and so on. When we look at the current state of privacy or data protection by design, however, we largely see activities that focus on the principles of data minimization and security. What we barely see are technical approaches for privacy or data protection by design that address all the other principles like lawfulness, like transparency, purpose limitation, storage limitation, and so on. All these principles also need to be addressed technically, but at least currently, there are way less activities on these principles. Of these, I will herein concentrate on the principle of purpose limitation and demonstrate how it can be addressed technically. The principle of purpose limitation is codified in Article 5(1)(b) of the GDPR, saying that personal data shall be collected for specified explicit and legitimate purposes, and that it shall not be further processed in a manner that is incompatible with those purposes. Implementing this principle in a technical way through technical mechanisms requires instruments that allow us to control the data access and the data usage based on purposes. In the technical domain, this is discussed under the term of purpose-based access control. As already said before, several proposals for implementing the concept of purpose-based access control technically have been made in the past. At closer inspection, most of these proposals follow a similar scheme. All of them start with a particular single database like IBM DB2 or MySQL or so on, and then employ the access control mechanisms of this database. They extend these access control mechanisms of the database with PBAC functionality, with purpose-based access control functionality, and then propose that the application uses this PBAC functionality to access data for a particular purpose. So with several such proposals already existing, the question arises why purpose-based access control is not in omnipresent use in practice. We analyzed this in some more detail and identified at least two main reasons for this. First, we identified several conceptual misfits between existing purpose-based access control proposals on the one hand and the realities in the form of practices, patterns, and so on that we know from the field of real-world application engineering. In addition to this, current proposals are typically limited to one particular database, which significantly restricts developers' choice of database and their flexibility, and it raises substantial risk of being locked into one particular database once it has been chosen. Beyond this, we also identified several further reasons that add up to this. For these reasons, see the paper. So what was our goal? We wanted to provide a reusable solution for purpose-based access control that actually reflects prevailing principles and patterns known from the field of real-world applications engineering. We wanted our solution to not be confined to a particular database. Of course, our solution has to provide the necessary functionality for achieving legal compliance depending on the particular use case. And finally, we wanted our approach and our solution to integrate well with established development practices in order to limit implementation and adoption efforts and therefore to increase the probability of our approach being adopted in practice. Again, we identified some further requirements in more detail, and again, if you're interested in these, please see the paper. So what does it mean when we say we want our approach to reflect prevailing principles and patterns of real-world applications engineering? Real-world application architectures are usually considered to be organized in layers. At least, we can distinguish three such main layers, namely the data layer, the application layer, and the presentation layer. Of these, the data layer is responsible for storing and organizing the data as such in databases, in cloud storage, in file system storage, and so on. The application layer, which sits on top of the data layer, comprises two sublayers. The business sublayer contains all the business logic and all the codified business objects and so on. And the persistence sublayer is responsible for mediating between the business layer and the data storage layer. Finally, the presentation layer sits on top of the application layer and is responsible for producing different presentations of the application to different interfaces. For instance, the presentation layer produces the user interface of a human user sitting in front of the system. It may also produce a XML representation of the data, or it may provide an API interface for accessing data, and so on and so on. These layers are typically considered to be independent from each other and as communicating through well-defined interfaces. To illuminate one of the conceptual misfits between existing purpose-based access control proposals and real-world applications engineering, let's look in some more detail at the communication between the persistence sublayer of the application layer and the data layer. In real-world applications, this communication is implemented as depicted here. Basically, the application uses exactly one user that connects to the database and then handles all interactions with the data layer under this particular single username. So an application only has one user, namely the application itself, communicating with the database and performing all data access and all other data operations. So real-world systems do therefore not employ the database mechanisms for managing users and for controlling data access and so on. Instead, the application in its entirety appears as one single user to the database. Users of the application and their access rights, in turn, are in real-world applications typically managed and enforced within the application layer without any involvement of databases or the data layer at all. This obviously conflicts with the prevailing approach of purpose-based access control mechanisms, which are implemented as extensions to a database access control system. Instead of implementing purpose-based access control on a database layer, we therefore propose to implement purpose-based access control within the application layer in order to achieve a way better fit with existing practices of real-world application engineering. In addition, we wanted our purpose-based access control mechanisms to be not confined to a particular database and to integrate well with established development practices in order to limit implementation and adoption efforts. Let us again illuminate this based on the linkage between the application layer and the data layer. Here, it is often assumed that the application code contains loads of very low-level commands like basic SQL statements for handling and querying data, or even very low-level commands that are specific to one particular database in order to manage the particularities of that specific database. In real-world applications engineering, however, these particularities of the different databases are typically abstracted away through an additional component which is called the object relational mapper. Such object relational mappers are available in nearly every programming environment and stack, and they are responsible for implementing the interaction between the application and the database, abstracting away all the particularities and allowing developers to easily act upon business objects instead of having to care about low-level database interactions. Based on these abstractions, developers of real-world applications can easily change between different databases without having to substantially change the application code as such. Besides providing a comfortable interface to business objects and mapping them to database representations and storing them in databases, object relational mappers can thus operate on multiple different databases and allow to freely choose and switch between these different databases. Object relational mappers therefore appear as natural candidates for implementing our reusable and, first of all, database-independent purpose-based access control solution. Overall, our approach is therefore to implement purpose-based access control on the application layer through reusable extensions of widely used object relational mappers. Of course, this requires us to let these extensions actually provide the functionality that is required by developers to meet their case-specific purpose-related requirements. So, what does it mean to provide the functionality that is necessary for achieving legal compliance with regard to purpose limitation? Again, we did a quite extensive requirements analysis on this. The results are again reported in detail in the paper and in another paper that is referenced here. Generally speaking, however, we want to have the capability to flexibly define purpose vocabularies instead of striving for a global purpose ontology that covers all purposes that might appear wherever and in whatever context, which is basically unrealistic. And on the other hand, we also want to be more flexible and more expressive than what we know and see from existing approaches that build upon quite limited and constrained sets of well-defined purposes like we know it from P3P, for example. So what we want to have is the capability to flexibly define a purpose vocabulary and possibly to standardize this in a domain or sector-specific way or so. Second, we want to be able to express hierarchies of purposes with different levels of specificity so that we are able to express more generic purposes like research in general, and more specific, detailed purposes like a certain piece of data may only be used for the purpose of epidemiological COVID-19 research or so. So we want to have the capability to express such hierarchies of purposes. And finally, we want to be able to combine allowed and prohibited purposes so that we can, for instance, express something like a certain piece of data may be used for all research-related purposes except for military research, so that we are able to combine a whitelisting and a blacklisting approach with each other. So based on our previous conceptualization and the more detailed requirements analysis, we provide two proof of concept implementations for two different programming frameworks and stacks. First, we extend the active record object relational mapper from the Ruby on Rails framework. And second, we provide an extension of the Sequelize ORM from the Node.js framework. Both ORMs already support a couple of databases, and the frameworks are broadly used in small and big companies. And to explain in some more detail what functionality our extensions actually provide, I will use the Ruby on Rails part. From the perspective of the developer, our additionally introduced functionality basically looks like this. Instead of searching for all user profiles matching the first name John, the developer can now perform the same query in a purpose-aware manner. The developer can, for instance, search for all usernames or all user profiles matching the first name John, and that may be used for a particular purpose like whatever. Our modified object relational mapper will then only return those user profile instances that match the first name John and that may be used and accessed for that particular purpose. If no profile matches first name as well as purpose, the result will be empty. So what goes on under the hood? Let's first look at the plain object relational mapper without our extensions. As already mentioned before, the ORM is a component that communicates with one of the supported databases and can be employed from within the application code. The application code, for instance, can define a model and a class for users, each containing a first name and a last name and so on. And when this is done, the ORM automatically generates a respective table within the database with the name users and all the fields that are defined like the first name and the last name and so on. When we now start creating user objects in our application code, the object relational mapper automatically generates respective entries in the database. So we now have a database filled with entries for all the created users, their first names, their last names, and so on. In the next step, the developer might perform a query against the ORM, searching for all user profiles matching the first name John. The ORM will then return one entry, namely the entry with the ID 1, that has the first name John and the last name Doe. So now let's look at our extension. The first thing that we have to do in order to allow for purpose-aware queries is to provide the list or the dictionary that I talked about before of available purposes. In this case, this is done through a YAML-based configuration file where all available purposes are listed and made known to the purpose-aware ORM. If we now invoke the same application code in the ORM, the auto-generated database table looks slightly different. every column of the database now gets automatically a partner column that is used for holding the purposes that these respective entries may be accessed for. In the next step, the developer may perform a purpose-aware query against the extended ORM, for instance, searching for all user profiles matching the first name John for the purpose of marketing, which is the purpose with the ID 7, which you see on the left-hand side. In this case, the entry for John Doe, or at least the first name for John Doe, may not be accessed for the purpose of marketing, but for two different purposes. And for that reason, our ORM extension gives an empty result. So somewhat complicated under the hood, but from the perspective of the developer, the only change that is required in the code is this simple, small for addition defining for which purpose a given query is to be made. Finally, some words on the validation. Article 25 of the GDPR does clearly not obligate controllers to implement every possible technical measure, but rather makes this obligation dependent on the cost of implementation. These costs of implementation are clearly related to the overhead that is introduced by a particular measure, and knowing this overhead for our ORM extensions is therefore critical. We therefore wanted to know what overheads our ORM extensions actually introduce, and for this purpose created a very simple example application resembling a fitness use case. We filled this application with 1,000 users, each with a couple of daily step records and heart rate logs attached. We created 17 possible purposes, and we implemented two different ways for accessing this data. First, data could be accessed through a plain data API, and second, data could be accessed through a rendered HTML representation that resembles a very simplistic web user interface. We then benchmarked the achievable throughput with and without our extensions in line with well-known best practices of performance benchmarking, and came up with these results. So what do these results show us? The first thing that these results show us is that the relative overhead introduced by our purpose-aware ORM extensions strongly depends on the size of the queried and the returned data. With larger data sets like the heart rate data, the relative overhead decreases, whereas the relative overhead is more substantial for smaller data sets and fewer data sets. The second thing is that when we consider the whole application, including the HTML rendering and several further things that add up to this, the introduced overhead may become negligible because many other things consume all the performance of the overall system, and then the impact of our purpose-related extensions rather disappears or can disappear in certain settings. Finally, we can also see that the Node.js implementation has a significantly bigger overhead than the Ruby on Rails implementation, which can be basically attributed to a different way of implementation, which for the database people among us causes more join operations across different database tables. So there is a first candidate for adding performance-related optimizations here with a different programming model. So noteworthily, all these numbers have been measured without any performance optimizations being in place, so just as a first impression. And we are very confident that with explicit performance optimization, these numbers can get even way, way better. Lastly, we made both of our implementations available as open source software so that developers around the world can easily download and use them in their applications in order to make them purpose-aware and to implement purpose-based access control within real-world application scenarios. So, what can we conclude? First of all, privacy by design technologies must definitely align with established principles, patterns, and practices of real-world information systems engineering in order to be practically relevant and to be used by developers. Second, we herein presented a novel approach to purpose-based access control that is implemented on the application layer through the extension of well-known object relational mappers. Our novel approach thereby achieves a way better fit with layered architectures, it achieves database independence and a high level of developer friendliness. We also provide 2 exemplary proof-of-concept implementations of our novel approach, one for the Ruby on Rails stack and one for the Node.js stack, that are explicitly designed for minimal additional implementation effort, and they are made available as open source software free for everyone to use. Finally, we also measured the performance overhead that is introduced by our purpose-based access control extensions and came to the conclusion that these overheads might be considered reasonable for at least some use cases, even without any performance optimizations being in place. Coming back to my initial remarks, in this talk I primarily focused on technical mechanisms for privacy or data protection by design that address the data protection principle of purpose limitation. Purpose limitation is, however, not the only principle that deserves our attention with regard to the development of novel technical approaches. The same is also true for the other data protection principles like lawfulness, like transparency, like storage limitation, and so on. For all those principles, we can identify a hurting lack of existing approaches, of existing technologies for addressing them appropriately in real-world information systems engineering. So if any of you is interested in discussions about how this can be achieved, in discussions on how we can address those principles, how we can employ technology for making privacy and data protection by design beyond the well-known principles of data minimization and security, any discussion in this regard is highly welcome. So just contact me, get in touch. I would be super lucky to discuss such things with folks from around the world. I can be reached on different channels. I have an email address, I have a website, I'm also on Twitter, so if you want to catch me there, get on. The same is also true in case you have any questions or remarks on this talk here. These are highly welcome, of course. Just get in touch with me, let me know what you think. Thanks for listening, even in hard and tough times. And then there is just one final slide that is obligatory. Here are the sources that I used in this talk. Thanks for listening. Thanks for watching. Stay safe, stay healthy, and get in touch.